G'day viewers. In this segment we'll talk about routing when there are multiple parties in the network which may have different policies. This is how BGP works. Okay, so our topic here is really to extend the routing we've seen in one major respect, and that's to allow the network to be composed of different parties who may have different interests. We'll see that's a big complicating factor in routing. This is one of the key pieces we need to get to internet-wide routing, to understand how it finally works, using BGP as the protocol we'll see. And the different parties here are going to be some of the different ISPs, for instance, that are in this diagram. Okay, so before we dive into the details, let's look a little bit at the structure of the internet, at least the structure as we need to understand routing when policy considerations come into play. Now this is a little bit of a messy picture, but all I'm trying to remind you of here is that we have individual networks. Now they could be ISP networks, content distribution networks, enterprise networks, and so forth. Within those networks, there are destinations we can route towards, and they are groups of hosts which are represented with IP prefixes. So these networks, and there are many of them, are themselves richly interconnected. They have different links between one another, often directly, and many times the link goes via these ISPs or Internet Exchange Points. These are facilities in the internet where if everyone drags a wire there, we can all connect them to the same switches and exchange packets. So through these means we have many connections between the internet, between all of the different networks. The whole collection is the internet. We now want to know how to route across it. And we can't directly use the techniques we've seen before because these different networks are owned and operated by different parties, and they may have very different ideas about what they want to do. So actually let me recap some of that. As we look at extending the routing we have already to this new setting where there are many different networks and we're working across the internet at large, there are really two problems that we're going to have to deal with. Two complications beyond what we know. The first one is this scaling. We want to be able to run routing on very large networks. To do that, we're going to need techniques which will help scale the routing process itself so that the table won't be huge and we won't spend too much effort working out the routes. We'll need techniques like IP prefixes, hierarchy, and prefix aggregation. Luckily, we've already seen all these techniques, so you'll simply apply them. And we're done on that side of the house. The issue we're going to look at in this video is the other major problem, and that's incorporating into the routing decisions the fact that there are multiple different parties, and those parties can make their own policy decisions. Different parties, for instance, might care about different things and want to choose their routes in very different ways to suit their own needs. This is the big complicating factor that we'll look at. It's really quite interesting. Let's just take a look at some of the effects you can get. This is a network, so the overall network here has ISP-A on the left and ISP-B on the right joined together. That's our overall network or internet. And I just want to look at what can happen when this network is really made up of two ISPs, each of whom may want to route according to their own needs. So what are those needs going to be? Well, each ISP is going to choose routes so that they follow the shortest path within their own network without caring about what happens in the other network. Why? Well, they're out to run their own business, so they might serve their business interest best by minimizing the amount of their own network they need to carry traffic. That would be a sensible thing to do. Okay, well under these rules, what's going to happen if we send traffic from A2, this is one of these prefixes inside ISP-A, to prefix B1 and back again? Now, we're going to follow shortest distance within the ISP. So for ISP-A, it has to get the packet over to ISP-B. If we start here at prefix A2, the obvious place to go to is this link between the two ISPs, because that's closest to where you were in prefix A2, where it happened to be located in the network. We go over this peering link, and then we have to go within this network. We'll follow the shortest path to get to B1. So we'll go somewhere like this. Wow, okay. Let's look at what happens the other way. If we're at B1 and we want to send traffic back to A2, what do? We do the reverse. ISP B wants to get traffic to ISP A because that's where the destination is. From B1, it will follow the closest prefix. That is here. It'll go to this peering link, across it, and then down within the network. Okay, well, interesting. We've chosen different paths in each direction. Not only that, but look, let's consider what the best path would be. The shortest distance I can see between these two paths is this line over this other peering link in the middle between them. Wow. Okay, let me clean this up a little bit. Here's a better diagram. And you can see that when we treated these parties independently, we actually selected paths that are longer than the overall shortest path. We did that in both directions, so we didn't really win in either direction. Looks like the direction A2 to B1 was a little worse, it was even longer. And not only did we take longer paths, but we've ended up, with asymmetric paths. It should say asymmetric. So the route from A2 to B1 is different than the route from B1 to A2 in reverse, which is something you might not have expected in networks, that going between, that your packets can follow different routes in different directions. But really, what's happening here is a consequence of the independent parties making different decisions. You might imagine we could get some of these decisions if we simply had hierarchy and didn't know what was going on inside one network. But even if we did, the independent parties lead to and the criteria I put forward lead to these same kind of routes. So what I'd like to move on onto now is routing policy. I talked just about some of the effects of independent parties, but let's talk a little more about what kinds of policies these different parties would like to enforce. What is it they really want to do when they select routes? Actually, the first thing to say is it could be anything. Policy really captures the goals of the different parties, and that depends on, whatever you want it to depend on. There's many different policies as there are different companies. An example of a policy that you might not have thought of, for instance, is that Internet 2, the educational network in the United States, provides connectivity between educational institutions, but it doesn't allow commercial traffic to be carried over that network. So commercial traffic will just have to go via other networks. That's an interesting restriction. This is actually not a technical restriction. There's nothing about the protocols that said this had to be the case. It's simply a restriction on the use of the network put forward by the owner of the network. So as you can imagine, there can be many different kinds of policies like this. However, since policy is such a nebulous word, we'll look at two fairly common, generic policies. The first one is a transit policy, where ISPs provide transit service to their customers. And the second one is what's called a peer service policy, where ISPs provide peer service to each other. I haven't explained what those policies are yet. We'll look at both of them in a little detail. So here is a transit policy. Now, with a transit routing policy, one party, we'll call that party the customer here, is going to get transit service from another party, and we'll call that other party the ISP. The idea with transit service is that the ISP is going to accept traffic for the customer from the rest of the internet. So here, the ISP here is going to accept traffic incoming from the rest of the internet that's destined to this particular customer. And the ISP is also going to take traffic from the customer to send to the rest of the internet, to any other destination on the internet. And the customer is really getting transit service from the ISP here. The customer is going to pay for the privilege. When you have connectivity to the internet by your ISP, for instance, you pay different amounts depending on the bandwidth you get. But the real value you're getting from this connectivity is the ability to send packets anywhere else on the network and receive traffic from anywhere else on the network. It wouldn't be worth much if it was much faster but only allowed you to send to other customers of the ISP, for instance. So transit service is the service that an ISP provides to carry traffic to everywhere else on the internet. The other second kind of policy that's different than transit service is peer service. Now in peer service, both parties, and in this network I've drawn two ISPs, ISP A on the left and ISP B on the right, the other two parties, they're going to get peer service from one another. Each of these ISPs is going to accept traffic from the other ISP, but only for their customer. So you can see here, ISP A is going to accept traffic that's destined to customer A2 from ISP B, and ISP B is going to accept traffic that's destined to customer B2 from ISP A. I hope I said that right. I hope I didn't switch one of those around, but I think you can see what I mean from the diagram here. What's not going to happen here is that ISP A, for instance, is not going to accept traffic from ISP B that's going somewhere else on the internet. That's not a peering policy. So I'm going to scribble all over that line. We don't allow that. Nope. Now, because ISP A and ISP B are really exchanging traffic for their customers, they're doing this for mutual benefit. And because they're doing that, often in a peering contract you won't pay. I do want to point out these are just generic examples of sensible policies based on business needs. But the actual contracts that ISPs have or other large networks have between one another are commercial contracts, they're proprietary. We don't know all of the details of these contracts, and they can be different in many small details, and it's private information. So now we know a couple of different policies that we might want to implement on a network. The kinds of policies ISPs would need to run their business and do things sensibly. What we don't know yet is how to actually implement any of these policies with a routing protocol on the network. Well, we're going to see that now. The routing protocol we'll look at to see how this is done in the internet today is BGP, the Border Gateway Protocol. This is the protocol which is used for internet-wide routing across ISPs. BGP is what's called an interdomain routing protocol. Interdomain means between domains, and the different domains are these different ISPs. Now, BGP is a path vector protocol. What's that? We haven't seen it? Well, path vector protocols are really just a variation on distance vector protocols. So all of that stuff you learned about distance vector protocols was useful. I'll go over, well, let's see. I think I'll go over some of this diagram in a little more detail later, but to just go over it briefly right now. What's happening here, this blue line represents a routing announcement that's going through the network. And if this were a distance vector protocol, we would carry on this announcement the destination, that's the prefix F1, and a distance to reach it, as well as a next hop, like the ISP. The IXP would be the next hop. Since this is a path vector protocol, we're going to carry the destination, the next hop, and also the path instead of a distance. The path here is you go via ISP B and then network F to reach prefix F1 from ISP A. Before we get too far, let's go into a little bit more BGP terminology so we can get the speak right. The different parties I've talked about here, the different domains, we can think of them as ISPs, but the language you'll see is ASs, where AS stands for Autonomous System, an independently operated network. We'll also use BGP to work out routes between the border routers of these ISPs. So we sort of have a split here where the routers, the ISPs are talking to one another via the border routers, which are running BGP and working out inter-domain routes. And we can use any old routing protocol we like to get around inside the network. That could be a protocol such as OSPF or ISIS that we've seen before when we looked at link state routing. The route announcements, which are sent out by the border routers in this network, are going to contain really what we saw in the previous figure. A prefix, the next hop, and this path vector instead of a distance. This path vector is simply a list of the ASs, autonomous systems, you have to go through on the way from where you are as the traffic goes through the network following that path in reverse to reach the prefix. The reason that a list is sent, the complete path instead of simply the distance, is to allow us to detect loops more easily. If you see a path that has the same AS repeated, that's a loop, so you don't want to use that path. If it's not, there's no loop. I'll also point out here, in case you hadn't thought of this before, that the routing announcements are going to propagate through the network with a distance vector or a path vector protocol in the opposite direction to the in which traffic is forwarded. So if the routing announcement goes from left to right, from one network to another, then if we want to follow that announcement, the traffic is going to go from right to left, back along that announcement. Okay, so let's look at a little bit more about how some of these path vector announcements are propagated. This is a little bit of a complicated diagram. I'll walk you through it. There are three ASs there. You can think of them as ISPs. AS1 on the left, AS2 in the middle, and AS3 on the right. Now, a routing announcement is being propagated for the prefix C in this direction, through here. As it leaves the first AS3, you can see that the announcement here says this is a route to prefix C. The AS path, so this is meant to be here, over this link, is AS3. That's the one you need to go through. And you send via the next hop of R3A, that's the border router, to reach to get inside AS3. As that announcement propagates through the network, and here it's shown leaving AS2, you can see that the path has changed. It's gotten a little longer. Now it says, well, to get here you go back through AS2 and then AS3 and then you're there. And there's a different next hop. You can ignore the last announcement. It's a little confusing. You might note that the path hasn't grown. That's because it's still inside the announcement, inside. Where are we? Inside AS1. Similarly, you can see down the bottom that there is an announcement for C that's also going out over another peering link, over another link, here through the network. It has the same AS path, but it has a different next hop because it's following a different link to get into that region, AS2, and a different link to get into that region, AS3. But these are really path vectors, and this diagram is trying to show you how they grow as the route announcement propagates through the network. Okay, now we're ready to understand how policy is implemented. We've talked about peering and transit policies. We just want to know how to implement them with BGP. BGP is a path vector protocol. We implement policies in two ways. The first thing we do is that the border routers of an ISP only announce to particular parties the paths that those parties are allowed to use. That is to say, we filter out the announcement of paths we don't want anyone to use. So we're applying policy by restricting the kind of connectivity and paths that we're offering to everyone else. That's most of what we'll see in the next slides. And the second effect is, within an ISP, if the border routers of that ISP hear multiple different routes to get to somewhere else, they can decide which route to use any which way they would like according to what is best for them. In a shortest path formulation, we would have to take the shortest path to get somewhere else. But with BGP, you don't. You simply take whatever's best by your criterion. So let's try and work through some examples of those policies and how they would be implemented. Here is a network I'm going to use. And you can see in this picture we have a big AS, AS1, that's the AS to which ASs 2, 3 and 4 connect to. They're probably paying AS1 to carry all of their packets and make sure that they get everywhere on the network. So that really means that AS2 as well as AS3 and AS4 is going to buy transit service from AS1. How's that going to work? Well, in transit service, now I'm going to look at AS2 connecting to AS1. So we're going to look at this transit service here, the announcements that go over here. AS1 is going to allow AS2 to send packets to anywhere else on the internet. To do that, AS1 needs to tell AS2 about all of the different places you can get and the paths it's making available. So AS1 will say to AS2, oh, there's this prefix out there, B, and you can send to it along the path AS1 and AS3. There's another prefix, C, you can send it to it along the path AS1 and AS4. AS1 won't try and advertise the route to prefix A back to itself. Actually, maybe it will, but it will be filtered out because we'll see immediately that it has a loop. So AS1 is announcing these routes to AS2. That's how AS2 gets to send packets out. And a similar thing is happening for AS1 announcing transit service to AS3 and AS1 announcing transit service to AS4. There's also the flip side of this that I've labeled customer in this diagram. It's the other side of the transit service agreement. We wanted to make sure, if we just look at AS2 getting transit from AS1, AS1, part of the deal was that it would take traffic, that it would route traffic from everywhere else in the internet to reach AS2 if anyone was trying to send to address A. So to do that, AS2 needs to tell AS1 that it has prefix A, and this is what it needs to allow traffic to reach. So it will send an announcement up to AS1 saying, hey, I have this prefix A, and you can reach it along the path AS2. Now, what will AS1 do with this? AS1 will announce that as part of transit to other parties. So for instance, it will tell AS4, hey, there's this prefix A. You can reach it along the path AS1, AS2. So that's with the flip side of transit. Now we've seen how transit's implemented. What about peering? Well as transit service in this diagram, you can see that AS2 and AS3 decided to peer to exchange some of their traffic for their customers, and AS3 and AS4 also decided to peer to exchange traffic for their customers. Let's just look at the AS2 and AS3 case. So what's going to happen is that AS2 is going to say to AS3 this announcement, AS2. That's really telling AS3, hey, there's this prefix A and you can send it along the path AS2 and that will get packets to prefix A. That's exactly what AS3 wants to do to get traffic to AS2's customers. Now on the other side, AS3 will say to AS2, B prefix via AS3. That will allow AS2 to send traffic to AS3 directly. And now we'll have traffic going from between here and here. You can see maybe now why we would do this. If we were to try and send traffic between AS2 and AS3 via AS1, we could do that. That's this high dotted path that I'm drawing. AS1 would happily do that for us. However, we have to pay AS1 to use it, so we would end up spending more money if we wanted to send our traffic through there. Instead, by peering, we can exchange our traffic over this other link directly, hide it from AS1 so that it doesn't need to charge it for us, and this is cheaper for us since we're both essentially saving one another money and giving one another a little bit of mutual benefit. Then we can do this for free to one another. And finally, just to complete the picture here, let's talk about what goes on deciding amongst the routes you get, not simply what you advertise out to other parties. So let's consider AS2 here. AS2 is going to hear routes to other places in the network, prefixes B and C. Let's think about prefix B. AS2 is actually going to hear two different routes to prefix B. One is the one that comes in via AS1. That was this transit here for B. And the other is the one that comes in for this peering service for B. So AS2 has a choice in how it will reach B. Which one should it choose? Well, it can choose whichever one it wants. It doesn't have to choose whichever one has the shortest path in any sense. And guess which one it's going to choose? It's going to choose the path directly via AS3. Why? Well, because this is the peering service, it's free, whereas you'll end up paying for transit. So in a hypothetical example, that's a pretty good reason to say why we would choose to send the traffic directly to AS3. Okay, well now you've seen the basics of how BGP works. BGP is actually quite a complex protocol, so there are many more details beyond these basics which make it quite difficult to understand. So we'll stop there at the moment. The bit we've covered is really the key ideas in BGP, And I think they're what's most exciting about it. What I would like you to take away here is that policy, the fact that there can be many independent parties and they can all have different and potentially conflicting goals, is a substantial factor that complicates internet-wide routing. It's a lot of the color, if you like, in BGP that makes it what it is and interesting. And it's even kind of not clear how well all of this works. You could ask, like, theoretically, is it possible for everyone to make independent decisions and yet still get some overall sensible path? Sometimes yes, sometimes no, actually. So what kinds of policies we can admit is a question there. There are also other important factors of BGP. We're not going into them in any detail now, but you could read about them or look in your text if you're interested, for example. I've just listed here some other factors you might want to think about. One is convergence, how well that works. We want routing protocols to adapt to failures. I didn't actually show you examples of this. It's much the same as other protocols. But we do want convergence to work well. We could look at scaling. I said we'll use all of these scaling techniques. You might simply be wondering how well it all works for internet routing. There's also some of the details of how you would integrate BGP routing across domains with some of the intradomain routing with OSPF or ISIS. As you can see, there's a lot of complexity here, but we'll stop here now that we've got the hang of basic routing between independent parties with policy.